Okay, this is ELEC1 2020, question 1, part A. A design for a logic system is shown below. For part 1, redesign the logic system using only 2 input and NAND gates. Draw a diagram showing your design and cross out all redundant gates. Well, there's a clue in terms of the last part, in terms of the number of redundant gate pairs that we should be able to find. The number of marks is 4, and that might suggest there's only 1 redundant gate. If you look back through enough past papers, normally it's 3 marks for actually drawing the NAND gate configuration, and then it's a mark for each of the redundant gate pairs. Hence, this might suggest there's only 1. Okay, so the first thing we need to do is map out the NAND gate configurations for each of the gates that we've been given. Now, I've just put out a block diagram here so that I can actually just remove each one. So the one which has an output J, let's just remove that. And so a single NAND gate for the NOT gate with both inputs attached. For output K, we've got exactly the same. And then for the AND gate with output L, hopefully you can remember the configuration for that is 2 NAND gates. And then we've obviously just got a single NAND gate at the bottom for output M. And then the OR gate is 3 NAND gates attached together. Now, all we now need to do is attach up the inputs as if they were the original configuration. So let's just do that. So the first of our attachments is across the top there. And then we can do the attachment across the bottom if we wanted to. The attachment from the output of the NAND gate and AND gate. And then we've got those cross attachments where A goes down to the NAND gate at the bottom and B goes up to attach to the AND gate. And then we just got to attach the output and the inputs to make sure that we've got our complete circuit diagram. Okay, now it's trying to recognize those redundant gates, and we're looking for pairs which are one after the other in the same line. They've got to be consecutive, and there's only one pair where you've got a NOT gates, so these NAND gates where they've got 2 inputs which are attached together, which are one after the other, and they're at the top here. Okay, so it's this one and this one. There's no other pair which are consecutive, one after the other. So what we're going to do is we're just going to highlight that these are redundant gates, and to do that, what we're going to do is we're just going to put a single line through each one. Okay, so part 2. So for part 2, complete the truth table for the original logic system. So they don't want you to do it for the NAND gate, they want you to do it for the original system because it could be ever so slightly different. Okay, so for J is the NOT of A, and therefore it's just going to be 1, 0, 1, 0. Okay, K is the NOT of B, so it's going to be 1, 1, 0, 0. Then we look at L. Well, L is the AND of B and J, and so that's going to give us 0, 0, 1, 0. So B and J. So we're looking for 2 highs to be a high output, and all other will give lows. M is the NAND of A and K. Well, remember in a NAND gate configuration, both inputs are high is the only time when the output is low. And so therefore we're probably going to end up with less lows than highs, and that's why we get 1, 0, 1, 1. And Q is the OR of L and M, and that gives us 1, 0, 1, 1. Right, so for the next part, write down the Boolean expression for the outputs L, M, and Q in terms of inputs B and A. Now, there are 2 ways of doing this. We can write out the Boolean expressions in full, or what we can do is use inspection to see if we can actually see a Boolean term which works. So if you're writing them out in full, when we look at L, there's only one high, and that is B is high and A is low. So it's going to be B and not A. Whereas when we look at M and Q, they're identical because we've got 1, 0, 1, 1 as the outputs. And therefore, we've got a slightly larger Boolean expression that we need to give. And so that is not B and not A, or B and not A, or B and A. And it's the same for Q. Now you get all 3 marks just for giving these expressions, because as I said, they don't want you to simplify. But if you use inspection instead, the latter two, you might have actually seen that you could have had this as an output, or even this. I think this is probably, if you were to simplify it using the original expressions, you probably end up with this. So both of those outputs could be these. Okay, part B. Now for part B, we've given a large truth table. Now, the diagram shows the circuit symbols through a 3-input exclusive OR gate. And we've got to complete the truth table. And you might think this is quite straightforward, but the reality is there's a bit of a trick as far as this question is concerned. Now, the reason you probably think this might be straightforward is if we look at 2-input AND gates and 3-input AND gates, they're very similar. That only when you've got all of the inputs are high is the output high. And you might think OR gates are the same, and NAND gates and NOR gates. But when it comes to exclusive OR gates, it doesn't follow the same pattern. This is something we need to be aware of. For an exclusive OR gate, what we need to do is we need to remember that, yes, it's the same in terms of circuit diagram, that a 3-input exclusive OR gate is 2-input exclusive OR gates attached together. But when you construct the truth table for an exclusive OR gate or exclusive NOR gate, you are going to have to go through the process of doing one of them and then the other. It's a combinational logic gate problem. Now, because it's a combinational logic gate problem, what we probably want to do is add in an extra column. And I'm going to do that, and I'm going to call it X. And this is going to be X for the position that I need to find out before I can do anything else. And what I'm going to do is call these A, B, and C. Okay, we're only looking at columns B and A, and the first 4 lines then repeat for lines 5 to 8. So it should be reasonably straightforward. So X is going to be 0, 1, 1, 0. Let me just bring that back for us. Let's just do that one more time so it's spaced out properly. 0, 1, 1, 0. And then it's going to repeat 0, 1, 1, 0. But now X feeds into a second exclusive OR gate, and so we've got C going in and we've got X going in, and we need to repeat the process. And what we end up with is 0, 1, 1, 0 at the top, but for the bottom half we end up with 1, 0, 0, 1. And so, as you can see, it doesn't follow the pattern that maybe the other gates follow as far as a 3-input gate's concerned. That concludes question 1.